Hey, what is up everybody? It is Mr. Boylan, and today, what in the heck are we gonna do in this video? Well, we are going to explain how chemical equilibrium reasoning can be used to describe the proton transfer reactions of acid-base chemistry. Okay, so there's a lot there. First of all, what the heck is an acid or a base? In order to understand what's going on in this video, we need to know what the heck an acid or a base is. So that's the very first thing we're going to do, and we're going to define an acid or a base according to both the Arrhenius and the Brønsted-Lowry definitions. Two, we are then going to identify what are known as conjugate acid-base pairs. Okay, so first thing we're going to do is define an acid or a base according to the Arrhenius definition. Very short, very sweet. Basically, if something is an acid according to the Arrhenius definition, it's going to be something that donates hydrogen ions in solution. So you put something in water, shoots out some hydrogen ions, it's an acid. An Arrhenius base, instead of increasing or donating hydrogen ions, it's going to increase or donate hydroxide ions, or OH ions. And as you look at your notes and on your screen there, you're given two examples of an Arrhenius acid, hydrochloric acid, HCl. When we put that sucker in water, it will donate a bunch of hydrogen ions. Notice though, sodium hydroxide is going to be classified as an Arrhenius base because putting that sucker in water gives us a bunch of hydroxide ions. So, acid, base, according to Arrhenius. Now, keep in mind something really important for this unit is that I will start using the hydrogen ion interchangeably with hydronium ion. Now, the reason why I'll do this is because those acids that are giving off hydrogen ions, or essentially protons, are really very attractive, and they are quickly picked up by water molecules to form hydronium. So, although we say or define an Arrhenius acid is something that will donate hydrogen ions, which is true, it's quickly picked up by water molecules to form hydronium. And so those two things are going to be used interchangeably here. So as you look at your notes, you can express hydrochloric acid in Arrhenius acid as something that donates a hydrogen ion, or you can think about hydrochloric acid in water is going to create a bunch of hydronium ions because that hydrogen is very quickly picked up by the water molecule. So as you think about how this might work, again, that hydrogen ion from the HCl molecule is going to get picked up very quickly by the water molecule to form hydronium. So again, hydrogen ion, hydronium ion used interchangeably throughout this entire unit. Now, we also need to talk about the Brønsted-Lowry definition of acids and bases. Acids, according to Brønsted-Lowry, are proton donors. Well, that's pretty much the exact same definition for an acid according to Arrhenius. So those two are kind of interchangeable. A Brønsted-Lowry base, however, is defined as something that's a proton acceptor, something that's going to gain a hydrogen ion or gain a proton. So the benefit, or one of the benefits of the Brønsted-Lowry definition is that it expands our definition of what things can be a base. It doesn't have to just have a hydroxide ion. And another really important advantage of Brønsted-Lowry theory is that it allows us to better illustrate the reversible reactions that we see very often in acid-base situations. Equilibrium. So notice that I have sort of a general equation here to represent a general acid or a proton donor, and I've got something to represent a general base or a proton acceptor. So I've got a very general equation here to represent an acid and a base. Remember, proton donor, proton acceptor. In the forward direction, boom, we donate that proton. It's accepted by the base. But just as importantly, if that reaction were to occur in reverse, we can now see how this thing will act as a proton donor and this thing will act as a proton acceptor or a base. So we've got a lot of this equilibrium stuff that's going to happen in this acid-base unit, and Brønsted-Lowry theory does a really good job of helping us to understand proton donors, proton acceptors, and the reversibility that we often see in acid-base chemistry. Okay, so this brings us to a very important concept, and that is the concept of acid-base conjugate pairs. And essentially, these are things that differ by the presence of a hydrogen ion. In other words, once something donates a proton, what is left? Or once something gains a proton, what has formed? So as you take a look at the example that you've got in your notes, We are only going to look at this in the forward direction, and we'll talk about why later. But recognize that in this example, in the forward direction, this thing, which is sulfuric acid, is going to act as an acid or a proton donor. Its conjugate base is what is left over after the proton has been donated. In this case, HSO4-, or the hydrogen sulfate ion. We also have water, which is acting as a base or a proton acceptor, and its conjugate acid, or what forms after the proton is accepted, which is the hydronium ion. So conjugate acid-base pairs. They're just two things, two species in the equation that differ by the presence of one hydrogen ion. Okay, let's take a quick look at a second example. This one we're going to look at both the forward and the reverse reactions to really better understand these conjugate acid-base pairs. We've got ammonia and water. In this example, in the forward direction, water is acting as an acid. It's acting as a proton donor. What's left, as we look at the product side, after it donates is the hydroxide ion. This is therefore its conjugate base. It's what's left after the proton is donated. As you look, there's another acid-base conjugate pair. The ammonia molecule is acting as a base, or it is accepting the proton from water. And what forms the ammonium ion, NH4+, is its conjugate acid. That is what has formed after it has accepted a proton. So we have two conjugate acid-base pairs here. However, let's look at this now in the reverse direction. The pairs have not changed, but now you just want to think about who's donating, who's accepting in the reverse direction. The ammonium ion is the acid. Its conjugate base in the reverse direction is ammonia. Remember, in the forward direction, this was our base, and its conjugate pair was the ammonium molecule. So same pair, we're just looking at it now in the reverse. We also have the second pair, water and a hydroxide ion. Again, in the reverse direction, this is acting as a base or a proton acceptor. The water molecule is its conjugate acid. It's what forms after that proton is accepted. So again, it's important to recognize these conjugate acid-base pairs in both the forward and the reverse direction. Then an important vocabulary word to keep in mind here when we talk about conjugate acid-base pairs is amphiprotic or amphoteric species. These are things that can behave as either acids or bases. Water is the prime example, but there are some other things that can act as both an acid or a base. So it's got to have something that has a hydrogen ion to start with, and it's got to have a lone pair of electrons to accept a hydrogen ion.